Okay, good afternoon. My name is Tony Mastroianni, and I'm going to be talking about taking 3D IC heterogeneous integration to mainstream. So I'm going to talk about tools and workflows, and particularly get into a little bit of the ecosystem to support that. So I work with Siemens EDA. I'm responsible for driving our 3D IC strategy and product solutions. So I always like to start these talks with defining a chiplet. Everyone talks about chiplet. A chiplet is an IC, an integrated circuit, that's been designed and optimized to be integrated into a package. Okay, traditional homogeneous ICs is a single chip in one package. Heterogeneous is multiple chips in one package. And heterogeneous design or package design, 3D IC, those are all terms that talk about putting multiple chips in a package. It is a very different approach from the traditional IC design process and packaging. So in an IC design, you design a chip, and then the package design basically just connects all of the inputs and outputs of that chip out so it goes on a PC board. But with heterogeneous integration, you're actually being able to take a system or a subsystem, decompose that into multiple chiplets, and connect those with inside the package. So this enables you to build systems or subsystems larger than you could do in a single chip, because you could do multiple chips. It also allows you to mix and match different technologies. So you can have one chip that's specialized for digital, another one for mixed signal, and you can even mix non-silicon technologies such as gallium arsenide. So it's another term is called Moore's law, more than Moore's law. So Moore's law, we're hitting kind of diminishing returns on how big we can make a chip. There are physical limitations, but also scaling. The transistors to make smaller and smaller means you could put more in a system, but we're hitting limits where we're getting, the cost is actually increasing, and we really can't, and the power is increasing. So the more this packaging technology enables us to extend some of the limits of Moore's law. So these types of designs require a significant amount of collaboration between a vast set of design tools. You have system tools. You have to worry about hardware and software and how you're partitioning that. You have to worry about the technologies for each that you're going to use for each of the chiplets. You have to worry about the packaging technologies. There's dozens of different package technologies. You have to worry about how you're testing these. It becomes much complicated because you're not testing a single chip, you're testing multiple chips, and you need the ability to test those. So it does require a totally different kind of design flow, and it also requires a different ecosystem to support this. So it's much more of a system approach to design these types of chips. So I mentioned you're decomposing a system into multiple chips. So we have to worry about how you partition the software, the hardware, what technologies you're going to put those chips into, what packaging technology. You have to worry about the simulation, functional simulation, and modeling. So this is all kind of on the system aspect. And then test. You also have to worry about how you're going to test the individual chiplets and how you're going to test the combination of the chiplets in a package. So all that needs to be carefully thought out and planned up front, very early in the design process. Now, there's many ways you can decompose that system. So to find the optimal way to do that, it really depends on the product you're trying to build, and that will drive the technology decisions that you make and the different approaches. So the other parts, once you start getting into the implementation, we get into the physical design, the physical verification, sign-off, and then we have electrical analysis. So this includes things like signal integrity analysis, power integrity analysis, as well as reliability type of analysis, where you're looking at thermal, mechanical stress type of considerations. So it really does require a very broad set of technologies integrated into a co-design environment. So this is not a serial approach where you're doing one step after the next. You're really iterating concurrently throughout the entire design process. So an important part also of supporting this is data management. You're dealing with a lot of data from different domains, and you have constant changing, so you need to make sure that's carefully orchestrated. And then you have to worry about the ecosystem and what I call design enablement. So I'm going to focus a little bit more on the design enablement and how that supports these heterogeneous flows. So I'll start with the CDX, Chiplet Design Exchange. This is a working group in OCP, the Open Compute Project. And really the charter of this group is to promote design methods, models, and an ecosystem. And this group is comprised of EDA vendors, fabs, OSAT, material providers, designers. So we have a broad cross-section of members that are actively working, and we're developing these different formats and standards. So some of the guiding principles we have is we want to leverage existing standards. So if there's standards out there, let's use them. There's no reason to reinvent the wheel. If there are new standards that need to be developed or existing standards that need to be modified, we'll do that as well. The other important concept is machine readable models. So it's very important. I think in the packaging world, a lot of the techniques have been using PDF type files, very ad hoc type of information. The semiconductor industry has been much more akin to using machine readable models. And the idea is your tools and your workflows can consume these models, and they can actually be used throughout the design process. The other important thing is we can create all these standards, but unless people are using them, they're really going to be useless. So we're trying to get adoption from the EDA vendors, the design community, as well as the supply chain, the fabs, the OSATs, the substrate providers, et cetera. So we're really targeting commercial as well as government opportunities. And heterogeneous is an important thing because heterogeneous gives us the ability to have multiple supply chains, different chip vendors, different substrate vendors, interposer vendors, all putting it together. So we need a common language to describe all the salient information required. And we also, it needs to work plug and play. So it's not a single it's not a single ecosystem. It has multiple users as well as suppliers. So the CDX group, we started out, the first thing that I was involved in was a white paper, and it was talking about if we have a chiplet, which I defined previously, what are the models that you need for that chiplet in order to design, integrate, verify that, and eventually release that into manufacturing into a package. So we put together a white paper that defined those recommended models, and we published that, and that got a lot of interest. There was another paper we did at OCP about a year later, and then we actually got that, we started working with JEDEC, and JEDEC actually extended their JEP 30 part model to include chiplets. So the part model was initially targeted to define components that would be used on a PCB system. So we extended that for chiplets, and that was initially released in January 2023 as an extension of the JEP standard. And then the most recent thing, we published a white paper on workflows. It's a little over 100 pages or so. So this is some good background information. If you're interested, I would encourage you to read some of these papers. So we'll talk about 3D IC design and development. I mentioned that the IC design community has been a very well-established design enablement system. So we have IP, SoC, Silicon on Chip IP. This includes your basic standard cells, memory, I/O, foundation IP. It also has analog mixed signal macros and high-speed I/Os. Okay, we also have process design kits. So these are all the technology files to describe the specific design rules for place and route, information for parasitics to do extraction, and other, most of the critical, this information is used to create the technology files for the specific EDA tools that are used in the design process. And this has been around for 20 years or so. So it's a very well-disciplined practice. And there's also schematic-driven layout macros for memories and analog cells. That's part of that as well. So for 3D IC design, this is really a new methodology. I'd say maybe with the advent of HBM memories, about 2015 or so, this is a very new problem. And there's very integrated, very large, broad set of tools that are needed. So we need a set of design kits that can support this. And that's what we're proposing. We call it 3D IC design kits, or 3DKs. And this really is a comprehensive set of design kits to support the design planning, the decomposition, the implementation, and the manufacturing and handoff of these designs. So that's what I'm going to talk about today. And some of the key components of that are CDKs. This is called the Chiplet Design Kit. This was built on the work where we defined the models and the deliverables for a chiplet. The other one is package assembly design kits. So this includes a bunch of different technology files that describe different rules for building the different components, defining the interconnect, as well as the connectivity. And then material design kits. This is a new area also that we've introduced. And when simulating, doing extractions, thermal simulations, signal power integrity analysis, you always have to worry about the materials for the different components in your system. And again, that information historically has been provided very ad hocly. It may be information that's coming directly from vendors. Designers are talking directly with the manufacturers, maybe PDFs or emails. What we're trying to do here is define a format to describe the material properties that are used for the analysis throughout the design flow. And again, these are machine-readable formats that can be used. So rather than having an engineer type this information from a PDF, we describe all these rules and material properties in a reusable format. And then if we get buy-in from all the EDA vendors, all their tools can support those material properties. And the last is package test design kits. So this is focused more on the test aspects. What are the test pins, and what is the how do you support wafer sort? So there's a different set of pins that are used for wafer sort, defining the different test modes. So that is another electronic format. So these different design kits that are in development are what comprise what we call the 3DKs. As I mentioned, the CDK is pretty much done. That is a JEDEC standard. So we're actively working on these other design kits in the OCP group. So I'll just start with the CDK. So the CDK, again, Chiplet Design Kit. These are the models. So we have thermal models. We have the test models. And you can see a lot of these are existing IEEE or JEDEC standards, IBIS models or IBIS AMI, .lib models for doing some top package level, SIP level, static timing analysis. And then we have CPM models, power models, and behavioral models. So these are all existing standards, and these are necessary. And this is a subset. There are different additional views there as well. And there still is a need for some level of documentation. So not everything can be machine readable. So you still need some documentation, but the idea is to minimize that where it makes sense. Security agents, trustability is important. We don't really have standards in there, but the idea is whatever security agents are included, just acknowledge that and document that in the part model. Now, the one area where we did not see existing standards was in the area of some of the physical models. So for physical models in the EDA industry, we have GDS and LEF and DEF, but it really doesn't get into the specific geometries and the tolerances. So that's where we went off and developed a new model. It's a JEDEC, it's an extension of the part model. So we have a physical model that does things like X, Y, Z coordinates. It has tolerances. It has a lot of the physical information. And also, we have an electrical model. So this has information kind of like an electronic data sheet. So it'll describe the different modes in a machine-readable format. We also include, for some of the interfaces, the standard interfaces that are used for die-to-die connections, things like HBM or UCIe Express, as well as your external interfaces, like DDR5 and SerDes type interfaces. What we've included in the electrical model for all of those standard high-speed interfaces is the naming, the standardized naming for those pin conventions. So when a chiplet developer is defining a part, they may have multiple interfaces. So they will have a unique pin name for the pins, but that can be mapped back to the standard names, and that can be useful throughout the design process. And I'll talk about a few examples there. So I mentioned the package test design kit. This is a new one, and that'll probably be an extension to this JEP30 model. Okay, so the first step in developing these 3D ICs is the architectural planning and analysis. So the 3DKs that we're talking about primarily are mostly in the CDK. So these are the behavioral models. You'll need some of the physical models and how the different components are available, the electrical models for the interfaces. So what you're doing during this architectural planning process is you're looking at different microarchitectures, and there may be multiple different design scenarios that would be applicable from a system or functionality perspective. But then you need to start looking at some of the technology implications. What ASIC technologies are you going to use? Or maybe not even ASIC or silicon, it may be non-silicon type technologies. So that's where you need to start collaborating with the physical designers and the package designers to decide, what those technologies are. So there's some collaboration that's required to come up with the particular scenario that makes most sense for your system, for the specific needs of your system, to pick the right technologies and the right microarchitecture. That really needs to get done up front, because once you get into the implementation, if you're implementing the wrong or non-optimal microarchitecture, by definition, you're not going to have an optimal design. An example here, I'm showing interface-based design. So this is leveraging some of that die connectivity that is defined in the actual part model for the chiplet. So you can develop scripts that would actually be able to generate some of the connectivity very efficiently to connect some of those high-speed interfaces, whether it's die-to-die or going outside the chip. Okay, this is an interesting slide. We call this package assembly design kits. Now again, when we're designing this, we have multiple manufacturing vendors involved in this, or potentially. So in this example, we have two different chiplet vendors, Fab 1 and Fab 2. We have an interposer fab that could be a separate manufacturer. Then you have your OSAT and you have your substrates. So many different manufacturing partners, and they all have their own set of manufacturing rules, right? And there's min-max ranges for pitches and all those connections. So one approach is you can have a predefined ecosystem where everything is worked out, and that's the recipe you use. But if we want to extend this model to the broad community where designers can pick and choose different vendors, we need a process to do that. And by having these machine-readable formats that can describe the rules, we can, for example, take a look at the two chiplet vendors, look at the rules for the pitch and the density for the micro bumps, and look for some overlap of where we can support a set of rules that will work in both manufacturing technologies. So that's kind of the intersection in that Venn diagram there. You also have to worry about the interposer manufacturer. So if you have some C4 bumps on the bottom or your micro bumps on the top, that needs to be compatible with the two different fabs. So those three cross sections will then drive your connectivity components for each of the chiplets. So define those bump definitions and the micro bumps and the C4 bumps to do that. And again, it may not be a specific value, there may be a range. And by having these machine routable models, you may actually even be able to include that in your optimization process where you can tune, get some better performance or reliability or whatever. So that's another advantage of having machine readable models. Again, looking at the interposer, you have to worry about what it's going to connect to on the substrate. You have to worry about the assembler. So the idea is we look at the manufacturing rules from all these vendors and then put together a common set of assembly design rules for each of the components in your package, your chiplets, your interposers, and your substrates. You'll also have your specific design constraints, and we also need to describe how all of these packaged components are assembled in an XYZ format, and that's what we call the 3D assembly design rules. So once you've defined these set of common assembly design rules, we can go off and build the EDA-specific design kits, the PDKs, to do the DRC, LVS, and extraction type checks, to do the physical verification. But the generic rules can be used for the physical design and implementation of these different components, as well as the assembly. Okay, so I mentioned there's two different kinds of analysis. So if we look at reliability analysis, two examples here are thermal analysis and thermal mechanical stress. So we need all the physical information of the chiplets, the dimensions, how they're stacked and interface, and the dimensions of all the connectivity connecting this together. But we also need the material design properties. So that's where the MDKs come in. So this is a machine readable format. So for each of the components that you're doing the analysis on, you need the appropriate or the applicable material properties to support that analysis. So for example, electric, if you're doing the signal integrity analysis, you need to worry about the TK, DF, dielectric constants, surface roughness, et cetera. For thermals, you worry about thermal connectivity, Young's modulus, and all those parameters. And these are used in conjunction with the information from the CDKs and as well as the 3D stack to do the analysis. When we look at electrical analysis, same thing. Well, the first thing for the different types of electrical analysis that we're supporting, and I have some examples, SI, IR, electromagnetic analysis, even electromagnetic analysis, and STA. So all of these require extractions. You have to do the extractions of the parasitics, which may include silicon and organic type interconnects. So we need to create the extraction decks. Well, we have that information defined between the assembly design kits and the material design kits. So they can be used to build the EDA-specific extraction decks that would be used to support the analysis. And then to do the actual analysis, again, you'll use the material properties from the MDKs and then the information in the chiplet design kits as applicable. And then test. So again, test, really, when you think about test, as a designer, and I am an IC designer by trade, designers normally think about what does the chip do and how does it function. So there is a functional mode for that chip, but it also has a separate mode, and there may be multiple test modes, and there may be a separate set of pins to test that. Particularly when you're testing those chips on a wafer, you have a different set of pins that are physically on that die that are used specifically to test just that wafer. They're not even packaged up. So that information needs to be included in these mechanical views as well as the electrical views. So in test mode XYZ, these are the pins that are applicable. And that information is then used to build the hardware testware. So it would be the probe cards and the test hardware. So they're the consumers who would use that type of information. We also include embedded analytics into the chiplets. So this is information that may get some information such as stress or temperature. You can also look at aging types of effects. So these embedded sensors typically are accessed through the test interfaces, your JTAG interfaces. So having this information is available, and also knowing where those sensors are in the chiplets is important, because if you're doing thermal analysis, you want to put your thermal sensors where the hot spots are. So that can become very useful as part of the design process. Okay, so now I'm going to talk about the JEP30 part model. So I talked about the CDK, and they are synonymous, but there is a subtle difference. So strictly speaking, the physical model and the electrical model, those are the JEDEC standards. Those are by definition what needs to be included in the JEP30 part model. All the other views that I talked about are necessary. What we do in the part model is we have a checklist. So this part model can be used by a chiplet designer and potentially a chiplet provider to define all the models. So maybe they want to provide those, so the part model actually can be used for a marketplace. But at a minimum, this gives the ability for end users to determine, what does the chip do? So the electrical data sheet, what are the physical models, and then what other models exist in the checklist. So the part model can also be used to enable a chiplet ecosystem. So chiplet suppliers. So again, we're trying to promote an ecosystem where we can have reusable chiplets, and they can provide all the relevant information for the chiplets, put it into the chiplet, and create a catalog, if you will. And then users and designers that are building systems out of these chiplets can browse that system. And it can also be used to actually to do a business transaction. So again, the chiplet model for looking at this to support an ecosystem. We have the part model can be used for people who are developing chiplets and want to market those in a chiplet marketplace. They can put them in an electronic catalog. And then your end users can shop around, and if there's different options, pick out the one that best meets their needs. And then they can use the models from that throughout the design process and take it all the way through to manufacturing handoff. So everything that I've talked about is kind of a comprehensive set of design kits. 3D Blocks is another initiative initiated by TSMC, but it is an alliance of the EDA vendors, and Intel is participating as well. And they have defined a lot of the mechanical models, the 3D stack, and the electrical views. So there is some overlap. What we're doing is a little bit broader in nature and is a little bit more focused in the design planning, implementation, as well as the manufacturing handoff. So some of these models can be directly translated. So the plan is we would have bidirectional translator that would be able to support some of the applicable formats that are compatible between 3D Blocks and the ADKs. And again, it's important that we get buy-in from the EDA vendors. So Siemens, Cadence, Synopsys, and Ansys are all actively working on these design kits. And another kind of recommendation that came out is it would be nice to have a single open source EDA neutral authoring tool to create these models. So we can't talk about any details now, but we have had some discussions where there will be an independent single tool that can be used to create these models, and these are CDMXL. They're really not something that you're going to want to sit down and write. So by having a single authoring tool that can create these EDA agnostic models and views, and they can be consumed by the respective EDA vendors directly out of those. So we'll be talking about that hopefully soon, what we're doing for that. So again, the ecosystem is very important. Just a plug here, we are announcing Siemens EDA has Innovator 3D IC. This is a complete set of 3D IC solutions. And if you're interested in finding out more information about some of these products, you could stop by our booth. And there was another presentation earlier today.